Assalamualaikum warahmatullahi wabarakatuh. Kita berjumpa kembali untuk melanjutkan pembahasan mengenai munculnya medan magnet yang diakibatkan oleh kawat berarus listrik. Pada tayangan sebelumnya, kita telah membahas mengenai hubungan arah arus listrik terhadap arah medan magnet yang ditimbulkan pada daerah di sekitar kawat berarus listrik tersebut. Tidak lama setelah penemuan Ørsted, ilmuwan Biot dan Savart mengeluarkan suatu hukum untuk menentukan besarnya medan magnet yang dihasilkan oleh kawat berarus listrik. Selanjutnya, silakan menyimak tayangan mengenai hukum Biot-Savart, yaitu dalam menentukan medan magnet yang dihasilkan oleh kawat berarus listrik.
Okay, now I'd like to tell you about the law of Biot-Savart. I don't think you pronounce the T actually, it's the law of Biot-Savart, or the magnetic field due to a current element. Okay, calculating the magnetic field due to a current element, you would use the law of Biot-Savart. Okay, so a current element, first of all, what is a current element? It's just one segment of a wire. Imagine that there's a whole bunch of wire going this way. So you got the whole wire going that way. But we're going to just look at one segment, and the segment we're going to have is going to be infinitesimally small. So we're going to call that length DL. Now I had to draw it big so that you could see it, but it's really going to be, when we do the math for this, we're going to assume that DL is really tiny, infinitesimally tiny. Now the current is heading this way, and let's just say it's heading straight down the way, and the current is I. Turns out that if you want to figure out the magnetic field due to this, just to this little current element, well, if you want to know it here, then you go from the center of your DL, you draw a vector R, and let's see, which way is it going to be heading? It's going to be heading, the field is going to be heading straight up. Yeah, that's right, straight up. And let's call this angle theta. The angle between the direction of DL. DL we're going to call, that's going to be a vector. It's going to be pointing in the same direction as I. So I need to sneak a vector sign in there for DL. Okay. Now to give the field just due to this little DL is really tiny. And so to remind ourselves that this is a field not for the whole wire, but just for DL, I'm going to put the field there. It's not a big field, it's a little field. It's dB field. Okay, so the dB, the little field, the very tiny field due to this little DL is going to equal, it's going to look very similar to the equation from the last video. It's going to be mu naught over 4 pi. Remember, this whole thing equals 1 times 10 to the negative 7th, and the units on that are Teslas, meters over amps. So I'll write that here, mu naught over 4 pi. That's going to be 1 times 10 to the negative 7th, and the units on that is Teslas, meters over amps, and you'll see why that has to be Teslas, meters over amps in a little bit. A different video actually. Okay, so this is mu naught over 4 pi, and then times I times DL cross R, or we can say I DL sine of theta all over R squared. So this looks a lot like QV sine of theta over R squared, except we're going to have the I times DL times the sine of theta over R squared. There's a cross product in here. You could say it's I DL, that vector, cross R, and then you would have an R cubed down here. Another way to do that also is to use a unit vector, and I won't go into that, but maybe your book has I DL cross a unit vector, and the unit vector has a magnitude of 1, so that's why that's still just R squared down here. Okay, well, in any case, the magnetic field due to this current element is going to be just a constant times how big the current is times DL times the sine of theta, the angle that it makes, all over R squared, R being the distance from the center of the DL to where you want to find the field. Okay, so let me show you how this works for a long wire charge, the magnetic field due to a long line of current going. Let's have the wire be going this way. So here's a wire, and it's infinitely long both ways. And I'm going to put a coordinate system on here. There we are. And let's say we want to know the field due to this wire. And let's say this distance from here, there's a distance A away from the wire. And let's say the current is heading up. So the I is up. That's the I. And right now I know that the field, the direction of the field right there is going to be into the page. So if I put a compass right here, if I put a compass there, it's going to point down. If I put a compass on this side, it will point up. Okay, but I'd like to know what the field is there, the strength of the field. Okay, so I'm going to make a little DL, and I'm going to find the field due to that little DL. That field due to that little DL is this. I'm going to make a little DL. That's a little arrow I drew there. It's hey, I know I call it DL, but because I'm in the Y direction, how about I call that DY? And this is down here, a distance of Y down here. So it's down a distance Y from the origin, and it's the thickness of this little bit of wire is dy, or the height of that wire is dy. Okay, well, the r is this vector, and so to get the field due to that, it's going to be mu naught over 4 pi, just a constant. And now I'm going to do I times dl, but I changed the dl to dy since it's in the y direction. I times dy times the sine of theta all over the r squared. Okay, now I'm going to add up then for every circuit, for every current element, that each one of these has some effect on the field there. And so what I'm going to do is I'm going to just add them all up with an integral. But there's a problem when I do that. When I go to integrate this, you see how my differential is dy? But what else is changing? Depending on where I go, the theta changes. So if I'm right here, theta is 90 degrees. But if I'm down here, theta is smaller. So theta is changing. And so is r. R, how far away this is from the point I want, is changing. So I have a variable in r, a variable in theta, and my differentials in dy. So this is a problem. Okay, well, what we do is we're just going to put everything in terms of y. So I can put theta in terms of y, and I can put r squared in terms of y. It turns out that before I integrate, I'm going to do this. So bring this over. Use I. I is just a constant. It's a number that would be 4 amps or 1 amp or what have you. I'll have a dy there. But to get r squared, if I'd like to get r squared in terms of y, you see if this is r, that I can put that in terms of y with the Pythagorean theorem. Turns out that r is going to be equal to the square root of y squared plus a squared. And when I square that, I get this. So I just get that. And the theta, the sine of theta, is the opposite side over the adjacent side, or the hypotenuse. So sine of theta is the opposite side, a, over the hypotenuse, and the hypotenuse is r again. So it's going to be r squared plus a squared. This time I have to square root it. There's no square root here because remember we square that r. Okay, well, it turns out then that I can combine these a little bit. And so dB is equal to mu naught over 4 pi. And then I'm going to have I dy, a just being a constant. And then this can combine to y squared plus a squared to the 3/2 power. Okay, now I don't want just the field just due to this current element. So to get the field due to all of them, I'm going to sum up with an integral. I'm going to pull out all the constants, mu naught I a over 4 pi. And I'm going to sum up the dy over y squared plus a squared to the 3/2 power. And I'm going to start at in y equals negative infinity, and I'm not going to stop summing those to y equals infinity. We had this integral, and it got pretty complex in that I have all these constants in front of this integral, mu naught I a over 4 pi, and I'm trying to take the integral of dy over y squared plus a squared to the 3/2 power. And I'm integrating from y equals negative infinity, because our wire goes way down there, all the way to y equals positive infinity. But you know, when you go way down there or way up there, they hardly add anything to the field. They don't, because r is so huge. When you're way down there, the r is so huge that and the theta is so small that you hardly add anything. Well, I'm going to tell you, if you were kind of looking forward to seeing me solve this integral, I'm not going to do that. But if you went to a table of integrals, or if you plugged in this integral into your calculator, it could tell you what the answer to this is. The answer to this turns out just normal integration by substitution doesn't get this done, but maybe a little trigonometric substitution. And you get this. You get mu naught I over 2 pi a. Ain't that nice how it simplifies to mu naught I over 2 pi a, where a is just the distance that you are, if you drew a line from the point that you want to a line that was perpendicular to the wire, that's a. Okay, so there you have it. So it's mu naught I over 2 pi a. Now, next, I want to show you how this gets used with a different situation. Sometimes they have problems with the law of Biot-Savart that are much more simple to do than the last one. And so this is a very typical problem in AP Physics or in just introductory physics. Excuse me. So you'll see why it's a lot easier to do. You have a wire that is moving along like this. The current's moving along, and then it goes in this semicircular loop, and then it continues on its way. And they want to know the field right at this point. So the question is, what is B right there? Okay, let's figure out what direction it's going, first of all, the B. Well, it turns out that you see this part of the wire, it doesn't put any field right here. Nor does this wire. Because if you think about it, if this is your DL and this is your DR, do you see the angle between DL and DR is 0? And so when you use this equation, I dl sine of theta all over r squared, the angle theta is the angle between dl and r, and so that's going to be 0 degrees, and the sine of 0 degrees is 0. So there is no magnetic field from this part of the wire or this part of the wire. However, this part of the wire there is a magnetic field, but you get a lot of nice cancellations. Okay, for one, take a look. If this is my DL, the DL is going tangential there, and this is my R. You see what the angle is between DL and R? It's a right angle. That's 90 degrees. The whole time, no matter which part you're on, like if you're here or up here, DL and R are always at a right angle. So you can make this is really the sine of 90, which is just 1 the whole time. Okay. Another thing about this is that r, this vector r, never changes in size. It's always the same size, and so that you can treat as a constant too. For this path, it's always a constant a. And so let's see what we get when we do this. We get dB is equal to, let's pull out all the constants. Mu naught I is a constant. Sine of theta, I'll just call that 1. And then I got 4 pi, and our r happens to be a, and it's a squared. And then I'm going to sum up all the dLs. But when I add up all the dLs, if that's the only thing in my integral, what are all these dLs when I add them all up? These little distances, dLs. When I get done summing all those dLs, I'm thinking that what you get is the half of the circumference of a circle. So when you sum all those up, what you get is mu naught I all over 4 pi a squared. And then this integral is going to give me pi times a. Not 2 pi a, because this is just a half a circle, so it's just pi times a. So we can cancel out a pi and an a. So the field, oh, I'm sorry, I made a mistake here. When you integrate this, you get rid of, when you get the whole b. It's not just, this is just for one little b. But once you integrate it, then this becomes the total b. And so the total b is going to be equal to mu naught I all over 4a. How nice. How nice is that? It's mu naught I over 4a. Okay. So that's how you use the law of Biot-Savart. There's other things that you can do as well to make a fairly difficult problem become much easier. For instance, what if this went like this? What if instead of doing this, it came in like this? Let me get a white background. So here are 2 wires. Those are the 2 wires coming in. And then it circles around like this, and then it goes out that way. Well, you see this dl, it's always at a right angle to r. And so it's pretty much the same as the last problem. You can pull everything out of your integral. And when you sum up all these dl's, it turns into 2 pi a. So that's the only difference. Okay? So that's how you can apply the law of Biot-Savart in some simple situations. Thanks. Bye.
Demikianlah pembahasan mengenai medan magnet, yaitu mengenai eksperimen Ørsted dan hukum Biot-Savart. Semoga bermanfaat untuk kita semua. Sampai jumpa pada pembahasan selanjutnya. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.